we're going to find concave up, concave down intervals. All right, look at example 1. Find the intervals on which the function is concave up or concave down. So second derivative number line test, let's find the second derivative. Okay, this has been brought out of the denominator, makes it easier to integrate. We're going to use the chain rule. Derivative of the outside, drop the exponent by 1 to -2. Leave inside alone, multiply by the derivative of the inside. All right, I'm going to do a little cleanup before I go to the next derivative. Multiply -6 by 2x. We need to find the next derivative, so that looks like, actually, this one's going to be product rule with chain rule. Because now we have two factors, this one and this one. Second thought, I'm going to go with the quotient rule. So I'm going to rewrite f prime of x. If you want to do the product with the chain rule, that's fine. I'm just more comfortable with the quotient rule. The answer for the second derivative comes from squaring the denominator. That's going to take it to a fourth exponent. The numerator of the answer for the second derivative begins with the denominator, low, and then the derivative of the numerator, d high, derivative of the high, and the derivative there is -12 minus high d low. The high, -12x, times the derivative of the low. Well, that's the chain rule. Pull the 2 in front, drop the exponent to 1, multiply by the derivative of the inside to this chain rule. So let's do some cleanup. Distributing this negative through, it looks like we're going to have a positive. Let's see, 2 times 2x times 12x. So 2 times 2 times 12 will be 48x squared times x squared plus 3. Okay, so we're looking for what points, concave up and concave down. We need where the second derivative is 0. All right, so for the second derivative to be 0, it's really just a matter of where the numerator is 0, as long as the denominator is not 0. We don't want 0 or 0, that's indeterminate. At this point, I'm going to study this a little bit further and see that I can simplify. Actually, back up here, notice that all of the terms of the numerator and then our denominator share the common factor x squared plus 3. So I'm actually going to divide out an x squared plus 3, drop this to 3 of them. It comes out here. Remember, I can only do this if it's present, x squared plus 3, in all the terms. I couldn't just simplify these two if it wasn't here. And then I'm going to drop this one to a 1. So actually, this is a 3. All right, so let's look at the numerator. That might make it a little bit easier to deal with. Now I can just distribute the -12 through one of these, and I'd have -12x squared minus 36. This is completely gone. I divided it out, so plus 48x squared. All right. You do cross multiply, so 0 here equals, so again, like I said, it's just 0 equals the numerator. I'm going to clean up the numerator and get 36x squared minus 36. Okay, so factor out of 36 and then continue factoring. So either x is 1 or x is -1. Those are possible points of inflection, or at least the x coordinates of possible points of inflection. Okay, so let's do our double derivative number line. the original function is defined on all real numbers. All right, and doing test intervals, if I plug in like -2, back up here, probably maybe even right here, if I plug in -2 and square it, what is this, positive, times 36 is positive, and remember it was all over this denominator. Well, that denominator is always going to be positive, so it appears that we're going to have graph is concave up from -infinity to -1. Let's see what happens from -1 to 0. I'm going to plug in a 0 for x here. The result is -36. Again, back up here, I'd have a negative divided by positive, so that's going to be negative. And as it turns out, this test interval results in the graph being concave up again. So concave up, down, concave up. So f is concave up on, and I'm going to join the two intervals. You're asked to justify because f double prime is positive. That's why we did all that work. -1 because f double prime is negative. All right, let's look at example 2. Here we have a function. Where is the function concave down? Ooh, the numbers are ugly. I'm going to set it equal to 0. I'm going to look for the greatest common factor, the GCF. I'm going to pull out a 12. Continuing to factor. It's probably going to be -2 and -2. And if I check real quick, I'm doing a guess check. Okay, it looks like that's what it was. Okay, so the x values of the possible points of inflection are going to occur where these two are equal to 0, these two factors, so either x is 2/3 or x is 2. Do a double derivative number line. Once we do test values, just to save time, the graph is concave up, concave down, and then it's concave up. Okay, I'm looking for problem 3, but I see it's not on my note card that I got off the Dropbox. So in that case, okay, we'll just work with it. Okay, I'll just pretend it's there. All right, it tells us that the graph of f prime is given below. What are the x coordinates of the inflection points of f of x? Okay, so we're given f prime, and the first question is, what are the x coordinates of the inflection points of f? So f has POIs at x equal. Okay, well, we're interpreting points of inflection for f from an f prime graph. We look for the relative mins and maxes. So from the graph, you can clearly see that this is going to occur at x equals -3, x equals -1, and x equals 2. So these are the x coordinates at which we're going to have points of inflection on f as revealed to us through the f prime graph, and those being the x coordinates of the relative mins and maxes. All right, and question B says f of x must be concave down on which intervals? Justify your answer. So the regular graph f I'm going to put is concave down on -4 to -3 and the interval from -1 to 2. So just kind of observe the behavior of the f prime graph on those x values, those intervals, and you'll notice that f prime is decreasing, and that's your justification because the slope you're looking at is decreasing. The slope graph you're looking at, the function, the graph you're looking at is decreasing. All right, so a review of the second derivative test and then also points of inflection.